member at the Department of Operations Research and Financial Engineering. So it's a unique name, but we do optimization there. Okay, so I'm going to talk about how can we possibly solve Markov decision problems faster using randomized iterative algorithms. And also I'm hoping to make a connection with reinforcement learning. So let me begin. Okay. So this is the outline of my talk. So I'm going to start with a brief introduction to Markov decision process, all the terminologies and specifications. And then I want to give you an example of how to use basic stochastic first-order methods to solve Markov decision process by formulating the problem into a specific saddle point formulation. And that particular saddle point formulation is very nice in a way that we actually have a bilinear Lagrangian function, and we can use samples in the most efficient way to figure out the optimal policy. And this has a natural extension to reinforcement learning, and we can actually make a strong connection between runtime complexity for solving the computation problem and sample complexity for learning the optimal policy. So I'll explain later. And I'm also going to show you some recent works on computational complexity lower bound for solving MDP and some other related works on value iterations. Okay, so I'm going to jump into the technical formulation. Okay, so I would assume everyone knows Markov decision problems. Okay, so MDP is the most fundamental framework in stochastic control and reinforcement learning. It models a Markov chain which can be controlled by us. So basically, we have some finite discrete state space on which we have a random walk. And at each state, we can observe that state and apply some action. So we can decide on how to control the random walk in order to make ourselves happy. So if we look at most of these AI applications, I mean games like Tetris or poker, if we assume that I'm playing with a stationary opponent, or Go if I assume that I'm playing with, again, a stationary opponent, not an adaptive one. Okay, so as long as we are trying to make sequential decisions in a dynamic process in order to maximize some objective, then we fall into the regime of Markov decision process. Okay, so to describe a Markov decision problem, so we need to specify the transition probabilities from states to states under possible actions. So we are going to work with a finite state space S. And at each state, we are going to be looking at a set of actions A. So we are going to look at the same action set for each state. So now in order to specify the transition probabilities, we are actually looking at a tensor, which is a state by action by state tensor. And the dimensionality is S squared times A. Okay? And also, so say that we move from certain state I to J according to some action, and we generate some reward. So the reward is going to be, again, a function of state, action, and future state. And for simplicity, let's say that all rewards are bounded between 0 and 1. Okay. So if you give me all those values, those p values and the r values, then the problem is fully specified. We should be able to solve it. So now what is our objective? So the objective of MDP is basically I want to control my random walk on the state space in a way so that to maximize the cumulative return. And certain state transition is going to generate a score, right? For example, in Tetris, once we eliminate some line, we are going to make 1 point. And if we don't do anything, we're going to make 0 point. And then we want to maximize the expectation of total scores generated by this process. Okay. So mathematically speaking, the objective is here. So here I'm using a mixed objective so I can accommodate both discounted case with undiscounted case. But in the discounted case, essentially we're going to add a discount factor to penalize future rewards in order to make sure that the overall problem is contracted in a nice way. And in the more general case, without discount factor, So gamma would equal to 1. That would correspond to the case in which I actually want to control this process forever, and I want to make sure that the average score I get per each transition is maximized. So essentially, if we take gamma equals to 1, then this objective converges to the objective of undiscounted average reward MDP. But sometimes to make life easier, we just take a discount factor gamma to be strictly smaller than 1 to get contraction. Okay, so this is the MDP problem. Okay, so I'm going to focus on the computation complexity of the problem, meaning that I'm going to assume that I'm given all these model specifications. I know all the transition probabilities, all the rewards, and I just want to compute the optimal policy or to approximate it, and I care about runtime complexity. Okay. So again, so some background. So whenever we talk about Markov decision process, we need to define value functions. So let's do it again here. So we can define the value vector for finite states or value function for infinite states. Okay. So basically, the value is going to be the total cumulative return we can generate from this infinite process, starting from given state I. And the total value definitely depends on the initial state. So we have a function of values. Each corresponds to one particular state. And we have basically a value vector for each stationary policy pi. And the optimality condition of MDP is the well-known Bellman equation, which is an equation for the optimal value vector. So basically, Bellman equation basically says that we have to be doing optimally at every time step, taking into consideration all the infinite future. So this basically says that starting at state I want to choose some action A to maximize the sum of my immediate reward and future reward starting at the next time step. And in the discounted case, we have a discount factor, R gamma. Okay. So essentially, solving MDP boils down to solving the system of nonlinear equations. So they are equivalent. Okay, and also, if we just try to figure out the corresponding best A for each state I, we get the optimal policy, which is going to be a deterministic policy. Okay, so that's the background. So if we look at major approaches in Markov decision problems, or even more generally dynamic programming, okay, so I think the first two major approaches are going to be value iteration and policy iteration. They dated back to like 1950s. And then not long after the development of Bellman equation, people soon realized that Bellman equations are equivalent to linear programs, so we can also use linear programming method to solve it. So if we just look at all the deterministic algorithms or even randomized algorithms, including the best algorithm for LP, to solve Bellman equations, then we get all this runtime complexity. So here we are measuring the runtime in terms of number of arithmetic operations. Okay. And if we look at those four complexities, we notice that all of them are at least linear. Most of them are actually superlinear. So linear or superlinear with respect to the input size. So what is the input size? We call that input size is I squared A. Okay. And however, so if we look into the literature of reinforcement learning, like one of the most popular algorithms is Q-learning. And if we try to understand what Q-learning is doing, Q-learning is essentially a randomized version of value iteration. And by using Q-learning, it's possible to get a better sample complexity. But it's not clear how can we push this into a faster runtime complexity. So basically, the question we want to ask is, can we trade the precision of the exact policy for a better runtime? Say that I'm happy with 90% optimal policy, maybe 80%, and that's good enough. And I will be happy with such an approximate policy, and I really want my runtime to be way smaller than those super linear time complexity. Okay, so this is the motivation. So the answer is yes, otherwise I wouldn't raise that question. Okay, so now let's look at the linear program formulations of Bellman equation. Okay. Anyway, so essentially, if we take a closer look into the literatures about MDP and Bellman equations, we quickly realize that they are basically linear programs. So the primal formulation for the Bellman equation is in the value vector. Basically, I want to find value vectors to satisfy my Bellman equation. And by satisfying the Bellman equation, meaning that I want some of those inequalities to be 0. Okay. And similarly, we can also derive the dual problem. So the dual problem has a very nice physical interpretation. Oh, okay, cool. Okay. So the dual problem is also very natural in understanding MDP. So recall that in MDP, our objective is to find a policy in order to maximize the reward. Right? So let's consider average reward MDP. So my goal is simply that I want to maximize the average reward. So it's a singular value determined by pi, and I want to find such pi. So this is my objective, right? So we can derive the dual formulation very easily by checking the stationary distribution corresponding to our policy pi. So I'm going to let psi pi to be stationary distribution under policy pi, stationary distribution of states under policy pi. And I'm going to call R pi S to be the single state transition reward. Okay. So if we write it in this way, essentially my optimization problem becomes this. I want to find the stationary distribution over states together with one-step reward function to maximize their inner product, right? So, and I can free up my psi as a function of pi by optimizing jointly over psi and pi with a additional assumption that psi transpose equals to psi transpose p pi. Okay, so if we keep playing this game, and eventually I'm going to define my dual variable as a joint distribution of probability on the space of state and action pair. So mu of S and A is the probability for S to occur, and also times the probability for me to choose action A conditioned on state S. So after we do this transformation, we notice that all this psi and pi, they disappear, and this entire program becomes a linear program in mu. So this is the corresponding linear program in the discounted reward case. Okay. So essentially, we could be looking for the best value vector to match the Bellman equation, or we could be looking for the best stationary distribution in order to maximize my reward. And those two problems happen to be dual to each other. And we have a strong duality between optimal value and optimal policy, together with the optimal ergodic distribution over states. Okay, so if we just use linear duality, we can easily realize that, okay, now in order to solve the primal problem, basically I want to find those constraints that are active at the optimal solution. And in the dual setting, it means that I want to find certain coordinates of my dual variable that achieve 0. So essentially, I'm trying to find the basis of my dual solution. So finding the optimal policy is equivalent to finding the basis of the extreme point solution in linear programming. Okay, so that's enough for the background. So now I'm going to develop the algorithm. So apparently, I want to solve the linear formulations of Bellman equation, but I'm going to focus on the undiscounted case for now for simplicity. But because I discard the discount factor, so I lose nice boundedness and contractiveness. So I'm going to make additional assumptions on the stochastic process so that I'm working with a reasonable class of problems. So I'm going to make two assumptions. The first assumption is going to say that I'm going to look at problems in which all the policies are going to generate somewhat similar stationary distributions. So basically, I want the stationary distributions under some policy pi to be varying within certain range, so they cannot be too far away from each other. So this basically requires that my policies should be relatively similar and sufficiently ergodic. And second condition is I want my Markov decision process to be rapidly mixing. So I'm going to assume that I know a uniform upper bound on the mixing time of the Markov chain under all stationary policies. An alternative way to understand this is maybe my original problem does not satisfy those conditions, but I'm going to focus on policies that are within such range. And I'm going to be looking for the best policy from that range. Okay. So now let's continue with our linear programming formulation. So we wrote down the primal and the dual, so naturally we can write down the min-max formulation using Lagrangian duality. And this is the Lagrangian function in the case when there's no discount factor, gamma equals 1, so some terms cancel off, which I like. Okay, so this is a very nice objective function. So essentially it's bilinear in mu, my dual variable, and also linear in v, which is my primal variable, the value vector. Okay, so the reason for me to make those assumptions is I want to bound the complexity for search spaces of this problem. So I'm going to construct a search set for the value function and a search set for the dual variable, which is a distribution over all policies and its corresponding stationary distributions. Okay, so basically, if I know that my problem is rapid mixing, then I should be able to know that my value function is bounded in an L infinity ball with radius 2 times the mixing time. And similarly, I also know that my dual variable is going to be a distribution over state action pairs, so it belongs to a simplex. And if I have additional ergodic assumptions, I can put in my prior knowledge here. So basically, this is a very flexible formulation in which I can incorporate prior knowledge about distributions over policies and about value functions, or even say that I'm doing imitation learning. I know something about what the stationary distributions should look like. Then I can put this knowledge into my dual constraint. Okay, so that's good enough for my saddle point formulation. So now let's solve it. So the algorithm is very simple. So essentially, the algorithm is a stochastic gradient descent algorithm, but a primal dual version using a particular information projection in the dual space. So what's happening is, I know that my value function lies in an L infinity ball, so that part is easy. But I do know that my dual variable is actually a distribution. So in order to learn a distribution fast enough, the natural Bregman divergence is KL divergence. Okay, and I'm using multiplicative updates in the dual variable. So what's going on is, at every iteration, we can pick one single state action and state transition. That's all the information we need for one iteration. So we are going to be sampling I, A, and where's J? J. So that's all we need. And using I, A, and J, we can quickly calculate samples of the two random variables in my updates. And actually, both of them are vectors with one or two entries, only one or two non-zero entries. Okay. So it's really just a stochastic gradient descent iteration with particular construction. Okay. So this is what the algorithm looks like. So I just want to say that the algorithm is primal do and is also a coordinate descent algorithm because we are only updating a few coordinates at each iteration. This makes a lot of sense because we are only drawing a very small piece of information, one state transition per iteration. So we only have a few new bits in each sample, and we are only applying a few updates to a few coordinates. And also, if you look at this closely, so essentially this mimics actually do simplex method in a way that we are applying a soft pivot using multiplicative updates rather than a hard pivot like in do simplex. Okay. So now let's prove some result. So by analyzing the primal do convergence and using martingale concentration, and further by rounding the duality gap to error in the policy and doing all the tricks, we can show that it's possible to find an epsilon optimal policy in this runtime. And what's going on here is that, so my first term is pre-processing time. And my second term actually comes from running the algorithm. And I have some additional term due to policy evaluation, which is small. OK, so the first complexity is a nearly linear runtime complexity for solving MDP. Already faster when our requirement for epsilon is reasonably not super small. And furthermore, if we look at this complexity, what we don't like is the first term, S squared A. So this is a linear term. This will be sublinear, right? So however, it's possible that we get rid of this S squared A as long as the problem specifications are given in nice data structures. So because all I need is to be able to generate sample transition of the decision process. So what I care about is, can I generate state transitions in O1 time? So this is doable as long as we pre-process the data. In a way, for example, we can pre-process my distribution vectors into a binary tree so I can sample them using log n time. So that will be enough. Okay, so after applying all these techniques, this is the final result. So we can get a sublinear runtime complexity for approximately solving average reward Markov decision process. And notice that we do have this dependence on the range of stationary distributions tau and the mixing time of the process. And I am not sure whether this part is improvable or not. But the good news is actually for large-scale MDP, this runtime could be even smaller than the size of the input. So we can approximately solve it without reading all the input bits. OK, so that's for the computation problem of MDP. So I just want to say a little bit that the method I just described also apply to the reinforcement learning setting because it is naturally an algorithm that uses sample transitions to make updates. So the difference between reinforcement learning and Markov decision process is the following. So when we talk about MDP, we are in the computational world, and we are given all the numerical values of transition probabilities and the rewards. So we know all those values. And now in the world of reinforcement learning, we only have a simulator of the game, in the sense that we can only choose state and actions. And sometimes we cannot even choose state. We can just play this game and try different actions and observe what happens on the path of the game. So this is the setting of reinforcement learning. Again, we want to solve the same mathematical problem, but we can only access information by playing this game. OK. Oh, by the way, so popular methods in reinforcement learning, like Q-learning and temporal difference learning, are essentially randomized versions of value iteration, while actor critic and policy gradient are essentially randomized versions of policy iteration. And there are also many other versions like A3C, DQN. They are those algorithms together with deep learning or some other parametric functions. OK. So, but let's continue with the tabular case without any parameterization. So the high-level idea is to apply this primal-do randomized algorithm in a way so that I'm going to play this game on a single game path, and I'm going to make updates as long as I observe a significant number of distinct states, and then I make the updates, and then I keep doing this. Okay. So this algorithm is model-free because we never have to estimate the transition probabilities, which are not known. We only need to update the value estimate and the policy updates the policy estimates directly. Okay. So in the setting of reinforcement learning, we care about a slightly different notion of complexity. So because now we are going to be playing this game once, but we are going to play it on an infinite sample path. So now I care about how many mistakes the algorithm is going to make before it becomes epsilon optimal in all future moves. And that is called the sample complexity of exploration. And now, due to the dependency on a single sample path, we are going to add a little bit to this complexity. We add a factor of mixing time and the square root factor of that tau parameter. However, if we compare the complexity of this primal-do method with the delayed Q-learning, which is the only sample complexity of exploration for Q-learning that I know about, okay, and we note that this one is definitely better than delayed Q-learning for certain values of epsilon, and my work applies to the undiscounted case, so it's a little hard to compare the dependence on other parameters. Okay. Okay. So I just want to say that by using this type of primal-do method with online learning, we can already achieve optimal sample complexity in this dimension, in the dependence on state space dimension, action space dimension, and epsilon. And also, we can characterize how the mixing time, how slow the process is, and also what is the range of the decision process. We can characterize how those parameters change, play a role in the complexity of learning the optimal policy. And definitely, I think what is to be improved or to be better understood is whether the assumptions on mixing time is too restrictive or not. It's not clear where the lower bound lies. So for certain problems, when the process actually mixes rapidly, I think this algorithm is going to be pretty efficient. So rapidly mixing process, an example would be autonomous driving, because whenever we drive our car and we do something wrong, we're going to crash immediately. So a counterexample would be like if I search in a maze, I could be making a wrong move in the beginning, but it takes me a super long time to realize. So those two types of games are very different in terms of how fast they mix under reasonable policies. Okay. So okay. So what I just described are how to use the sampling mechanism to speed up the computation of an epsilon optimal policy for Markov decision process. And what makes me very curious was it looks like the data structure of the problem actually matters. Back to this slide. So notice that for the same problem, the runtime complexity is going to reduce from linear to sublinear if the data structures are good. So I want to explain why this matters, and I'm going to prove that the data structure matters not only in the upper bound for runtime complexity, but also in the lower bound for runtime complexity. So what's going on is this. So the algorithm is always going to be sample state as prime conditioned on current state and current action. So this is a critical step in the randomized algorithm. We are going to be simulating the process, and then we apply primordial updates to learn it. So in order to make the algorithm run fast, I want this step to be done in tilde 01 time. So how do I do this? Say that let me look at my vector of transition probabilities for a specific S and A. So say that this is my transition probability matrix. I have 1.1 here, 1.3 here, 1.2 here. So this is my probability vector. So if I want to sample from this probability vector, typically, if I don't do anything, the time I need is going to be OS. Okay. So, however, if I transform it into a cumulative distribution by simply doing this cumulative sum, then now if I want to generate state S transpose, state S prime, according to this cumulative distribution, I can simply generate a random variable uniformly from 0 and 1, and then do a binary search to locate the corresponding interval. And this can be done in O log S time. Okay. So this is a trivial result from, I don't know, theory of computing. So we can generate a sample from a discrete probability vector in nearly constant time. And for Markov decision process, our input happen to be such discrete probability vectors. So we want to pre-process them into cumulative distributions or binary trees or some other nice data structures to generate the samples. Okay, and now we get nearly 01 runtime for generating each sample. So this is important in a way that it draws a strong connection between runtime complexity for solving the computation problem and sample complexity for learning the optimal policy. So basically, as long as I get a nice learning algorithm, I should be able to adapt it into a fast computation algorithm because I can simulate the process super fast. Okay. So however, this phenomenon is curious. So why would data structures make the problem different? So that motivated me to look into lower bound of MDP. So basically, I want to understand how the lower bound of runtime complexity of Markov decision problems depend on the data structures. Then I look into the early literatures on Markov decision problems, and I barely found any lower bound. So I mean, so the closest lower bound will be like POMDP is p-space hard, but that's not a useful lower bound in my situation. And also, Cho and Tsitsipas, they have some information lower bound for smooth Hamilton-Jacobi equations. But in general, there's no computational complexity lower bound that tells me how many arithmetic operations I need to solve a given size problems. I do note that there are many sample complexity lower bounds in the literature of reinforcement learning, but you all know that sample complexity is different from computation complexity. Okay. So that is so we proved the lower bound. So the lower bound is, okay, the result reads very naively. So the lower bound basically says that you have to read most of entries in the data input in order to find a reasonable epsilon approximate policy. In the case when my probability vectors are given in this form, just a discrete vector of probabilities. Okay. So this lower bound is not surprising, although it takes, I don't know, many pages to prove, but it's not surprising at all. Okay. So so it's actually good because we have already shown that it's possible to solve MDP in nearly linear runtime. So the upper and lower bound nearly match. And second, let's look at special cases when my data are already pre-processed into cumulative distributions or binary trees. So actually, we look at both cases. And in those two cases, even the lower bound changes. So in those cases, the lower bound changes to SA over epsilon times some constant factor. So this is quite interesting. So if we put together the upper bounds in the case with standard input and the cumulative distribution input, together with the two lower bounds in the two different cases of data structures, both of them show that the complexity of MDP actually depends on data structures. And once we can sample using the later data structure, the problem becomes simpler. So it's a very interesting phase transition. And let me explain what the lower bound means. The lower bound means that no matter, you can use any algorithm, any randomized algorithm. But however, for any randomized algorithm, in order to get an epsilon optimal policy with a high probability, the algorithm needs at least this many queries from entries, which is a lower bound to runtime complexity. And same thing here. So they are actually lower bound for adaptive query size, not sample complexity. So they are stronger. Okay. Okay. So that's the lower bound, and my last page is something I just want to advocate for my collaborators. So, so basically, there's still a gap between upper and lower bound. So we try to close that gap. So one direction we are working on is we try to accelerate value iteration methods. So we do know that value iteration converges geometrically fast, but each iteration is going to be time-consuming due to calculating of all the inner products. So we want to use learning and randomization to accelerate that part. So we have two set of results for discounted problems. Okay. So it's possible that we use randomized value iteration to achieve, again, sublinear runtime for solving discounted MDP. And we have a force dependence on this discount factor. And this also requires assumption that my data is pre-processed in a way that I can directly sample, I can directly simulate the decision process. Okay, and alternatively, if we do not like this epsilon square dependence, alternatively, we can spend more time on pre-processing to get a high accuracy epsilon optimal solution. So an alternative solution is we can get a logarithm log 1 over epsilon dependence by doing a pre-processing every a few iterations. So this is a joint work with Aaron Sitford, Carrie Wu. Where's Carrie? And Carrie's here, and Yin Ye. Okay, and we are trying to push the limit and see whether we can close this gap. So a short summary is, it is really curious that runtime complexity of MDP actually depends on the data structures. And as you can see that once we can sample, then we can do a lot of those learning tricks. So I shouldn't say approximately equal, but I think sample complexity is definitely strongly related to runtime complexity for MDP. And that also means that reinforcement learning and the Markov decision process, they are similar problems. We want to look at them together. Okay. And also we know that there's definitely still a gap between the upper and lower bound. We have a gap, we miss one factor of epsilon, and also dependence on discount factor, mixing time, and range of ergodic distributions. All those dependencies are not clear yet. So that's the open question we have. Thank you very much.
Questions? So you mentioned, your first results were depending on the mixing time, right? So these new results don't depend on mixing time anymore?
So that result applies to the undiscounted problem. So without any discount factor, the problem is essentially unbounded. So I assume the mixing time and ergodicity. For example, if we consider a problem which could be mixing super slow, So within maybe the mixing time is, I don't know, several orders of the dimension of the input. So I have to really wait for a super long time before I observe anything useful. So that will be a case in which the mixing time really kills the problem. That makes sense? Yeah. But in the discounted case, once we have a discount factor, it means that when I look into the future, and from certain time on, all futures are going to be playing such a small role so I can ignore them. So basically, discount factor or mixing time, both of them are playing some cap on the time dependency of the process.
I guess like if you don't sample the problem, right, then you get the entire information, you might hope to not depend linearly on the mixing time.
Yeah, I think it's definitely, I wouldn't say definitely. Okay, I would say that in the case when we have to rely on samples, that dependence is actually optimal. I can prove a sample complexity lower bound. But in the case when we know all the input, it's possible to improve that dependence. That dependence is not good enough. Thank you.
Any more questions?
So usually the transitions between states is sparse. So do you have like bounds that depend on the sparsity of the transition matrix?
I do not, but I would say that, so essentially the current upper bounds are essentially linear with respect to the number of state action pairs. But however, the sparsity of transition would help in this part, in those algorithms in which we have to pre-process. Then we should be able to replace this quantity with the number of non-zeros. And that would make this complexity much nicer looking. Thank you.
More questions? If not, let's thank Mengdi.